this is the one that I really enjoyed because I could save money, and I'm kind of cheap. Here's the Talo bridge circuit again. It's in a little different orientation, but basically it's just a bridge. And the 351 ohm resistors are 3 legs of the bridge. The tuned part of your circuit is another part of the bridge, and then across the coil here is the indicator. That's all it does is indicate. The diode only allows current in one direction, and the LCD or the LED at the bottom, it tells you when it goes out or when it gets really dim, you know you've tuned your antenna circuit. Let's see now. First line is adjusting repeats to be purely resistive. We talked about that with tuners, but we can also change the feed line, or you can change your antenna. If you know that your whole system is slightly inductive, you can add a capacitive hat. Some of the more complex verticals have little hats on the top of wire. That's adding a little bit of capacitance to the top of them. And you might notice some of the stubs have more capacitance added than others to tune for all of our HF frequency, our HF bands. The other thing is you can add inductance by putting in a coil. This allows me to make my antenna shorter. The best place to put this is at the top. Trouble is, in the mobile situation, when you have that coil, this tends to start flopping and then you'll start breaking it. You will see base mounting, but that's probably the worst place to have it. So this is the best compromise for being in a mobile situation and to get the least amount of wasted power. Best would be the top, but your antenna won't last very long because it's vibrating so much it'll break. Let's see. Oh, this is an equation you will need to know. This is how you figure out how long your wire should be cut for 40 or 80 or 30 meters, whatever is your favorite band, if you want to make a resonant antenna. But you also need to figure in the velocity factor of the wire. And that is specific to the wires. You're going to have to look at the manufacturer's guidelines. You're going to have to look at the, when you want to know how long in wavelengths your feed line is, you're going to need to know the frequency you're at, or what band of frequencies you're at, and the velocity factor of this specific coax. And it varies by manufacturer, so you're going to have to get their spec sheet. I can say it's 99% or 95% or 90%. It could be even as low as 70, in the 70s. I've seen that. But you need to know it specifically for your make, model, brand, everything. So I can't really tell you what it is. That adds into this. It makes it electrically. The speed of light, that 299,792,458 meters per second is in a vacuum. This is not the speed of light in wire, not the speed of light in water. The same, or the speed of light in my glasses. That's why I can see with these things on, is because the speed of light changes as it goes through the refractive index. Some things might not want to see as well. So you need to know the velocity factor, and in this case it's called refractive index in water, air, or in my glasses.
Now this is, what's the,
What?
I've heard the term end effect on a wire antenna. The end effect
yeah.
has to do with the capacity or inductance or whatever you have at the end effect of the thing. I've basically seen those sometimes like.
It does change the velocity factor slightly,
Yeah.
but it's how accurate do you want to be? If you work out Ohm's law to the 5th place and you find your resistor only goes to the 2nd place,
Slide rule accuracy is usually good enough.
yeah, even a cheap slide rule accuracy is good enough. Because even at that point, your rule of thumb and, I have to cut and paste, and, well, I can only have this capacitor, but I have more range in resistors, and a variable resistor is cheaper than a variable capacitor, so maybe I add that to the circuit. You have to make all these compromises and change your calculations, just like I did with that Z-match tuner, wherever it is. It's right here.
Oh,
No, that's an LC tuner.
oh,
Either that or when you're designing your antenna, you cut the length of the wire the way you want it to be to match.
I advocate not making resonant antennas. I use tuners and make your tuner as efficient as possible, because then I have an antenna I can use on multiple bands. We're going to get to some radiation patterns a little bit later, and I'll show you where a dipole is a resonant antenna. It's got two legs and a single feed point. A doublet is the same system, but it's non-resonant. So when you get a G5RV, it might be resonant at a certain frequency, but it's 3/2 wavelength, and it allows me to work on almost all of the amateur HF bands. I can tune to all of them. And if mine were long enough, I could work on 160. But still tune 17 meters, 30 meters, 40. Let's see. Since this is a class on ecom antennas, this is the range of antennas that I wanted to cover and I think are the most used, ranging from our quarter wave vertical, which I'm not real proud of, but everybody seems to have one. I would advocate the next two over this one. They have better radiation patterns and they have more gain. You don't waste as much.
they're harder and harder, so
Not the 5/8.
J-phones.
You might be able to put it on there, maybe.
Mass mount, not a mag mount, but a mass mount. You can get
Some
on.
of my weak signal people have some really. I have seen a big a phased Yagi Uda on top of a car. I think they're a few screws loose, but hey,
Oh,
J-pole has gain?
as compared to this, yes. Normally you go compare everything to a dipole because that's the standard, and everybody says the isotropic antenna, but I've yet to see a real isotropic antenna.
Kind of hard to get one.
Yeah, they're theoretical. It's like a magnetic monopole. But the dipole, I can make one of those. So anyway, in order, I think, and this might not just be my opinion, but I think these are the most common to the least commonly used in econ. I want to advocate that people start thinking about single sideband, because 2 meters and 6 meters on single sideband is very useful. And if you're out in the bush and not in our Washington County Valley here, you can get out a lot better with this than you can with this. And besides, CW. It works, it's a TLA. And now we're going to go through my list of antennas here. I'm going to go through some pros and cons. I want to describe the antenna, a little bit of history on a few of them, and then I'm going to show you the radiation pattern. So we will go through each one of these antennas. One good thing about this is its pattern is omnidirectional. So I can talk to any one of you and not be preferential. It's very simple to set up. I can just stick this on a pie tin and put it in my window. Ubiquitous, yes, they really are everywhere. Be careful of the takeoff angle, or be knowledgeable of what the pattern is, because if you're on that mountaintop and you can easily stick this up in the air, you can get out to the people down below you much better. I want you to know what this antenna is doing and what the radiation pattern looks like so you can use it better. If this is really close to, say, a wall, a metal wall especially, or a beam, it will get detuned. It will tend to suck power away from the radiation pattern. If there's anything nearby, say wet trees, within, let's see here, there's the Fresnel and the Fraunhofer region, but they're basically called near field and far field. And I think near field goes out to 10 wavelengths away. Anything beyond 10 wavelengths away from the radiation point is considered far field. So you want to get this at least 10 wavelengths away, and not these condensed wavelengths, but the real 2 meters away from any problem. So putting it up on a mast is really good, but putting it next to a hemlock tree, a wet one, is not really good. Or even a tree, when it gets its sap running, it will change the radiation pattern.